Hello, everybody. Welcome back. Okay, so today we will keep talking about this new chapter for recurrent neural network. Okay, so I think last time we have gone through the basics for the forward pass and backward propagation for a recurrent for a simple recurrent neural network. Okay, and we've already seen that. Let me go back several slides ago. So the difference between a regular neural network with a recurrent architecture-based neural network is that the parameters at different time steps are shared. Okay, so the parameters used, the weight matrix used at current time step is the same one that's used in the previous time step. So that means the loss that we compute for one time step actually will affect the parameters several time steps ago. Okay. Because they are the same parameters. So in the backward propagation, we actually need to take an accumulative perspective, which is that we need to sum up all the gradients for each time step and use the summation of the gradients as the total or the final gradients to update all the parameters. Okay, so this is often a very time-consuming operation, right? Because you need to let the gradients at the current time step to back propagate all the way to the beginning. If we don't set any other additional constraint. Okay, so a common constraint that we put to the back propagation through time, which I don't show here, is that we will set a limit to how many steps we need to actually go back through time. Okay, so in the example here, if we look at the gradients in the yellow color, right? If we focus on the gradients for the weight matrix U. So we actually go 3 steps back, right? We go to the time step 3, which is the du at t equals 3 and du at t equals 2, and the du at the first time step. Okay, so we can, if we want to save some time, right, we can set a limit. Say we only go 2 time steps back. And if we set that limit, then we will not compute the du at time step 1. Okay, so these will not be computed. Okay, and also the dw at the first time step will also not be computed. Okay, so we saved some time by looking forward only 2 steps ago. Okay, so the back propagation through time is not carried out through the whole sequence. Okay, so this technique is called truncated back prop through time. Okay, and it is basically a default option for most kind of recurrent neural networks, right? Because we cannot afford the cost for back propagation through the whole sequence. And also, it is not a wise choice to go through the whole sequence, to back through the whole sequence, because not only because of the computation, but also it's not we're not gaining good effects by propagating through a long distance, because due to the sometimes the vanishing is the vanishing gradients and even the exploding gradients. So the effect would be so a long distance back propagation would not be that effective. Okay, so usually we will set a truncate threshold to this BPTT, back propagation through time. Okay, all right. So one thing about this is that in an actual implementation for a neural network, for recurrent neural network, we don't need to do the backpropagation manually, because just like a convolutional layer and a linear layer in PyTorch or other frameworks, the backpropagation is taken care automatically by the computational graph mechanism. All right. I think today we gonna go through a complete example for a language model. Okay, and I think if we have time, and I think so, we will go through the next section for the gated recurrent unit. Okay. All right. So a language modeling task or a language model is an important natural language processing task. It is commonly used in tasks like speech recognition and or in situations where language generation or language recognition are required. Okay, so for example, in the let's take the speech recognition example and say there are two sentences that are the candidates for the sentence being recognized, right? The first one is called "On the wall, I see a picture," right? And second is "On the wall, I see a picture." So these last two words, they sound very similar, right? But we know that the first sentence is more likely semantically, right? Because a picture is more likely to be observed, to be seen, right? Rather than a picture full of water, right? So that is a common sense perspective. Okay, so if we speak this, state this problem in terms of the language of modeling or language of probabilities, we can say that the probability of the first sentence is larger than the second sentence. Okay, and the numbers that are listed here, these are typical values generated by a language model. Okay, but these language are the numbers here are arbitrarily written here, but yeah, so you can notice that they are such small numbers. Okay, because the language model, the main reason is that the language model, a model contains probabilistic information for all the words in the training sets. Okay, and if we train a model with a pretty large training sets, then that means there will be hundreds of thousands or even millions of words in that data set, and the model will take everything into consideration. So the probability, for example, of the first word being on is itself a very small number, because there are a lot of many other possibilities for other words being the first word in a sentence, right? So we will later see that once we consider the probabilities for each word incrementally, and the probability of the whole sentence can be viewed as a product of all these small piece of probabilities, right? So if we multiplies a bunch of probabilities together, it will be the result will be even smaller probability. That's the main reason why we have pretty small numbers here. Yeah. So I think we will get a better idea once we gone through the example completely. Yeah, you can say that the longer sentences, the smaller the numbers. Yeah, because longer sentences are more difficult to model, right? The model is it's very easy for the model to guess that I'm going to say a one-word sentence like hi, right? Because hi is so commonly used as greetings. It appears a lot in daily conversation, so it's very easy to predict. But if I gonna say something complex, then it will be very hard for the model to guess. Okay, so we basically simplifies the purpose, the goal of a language model. So given a sentence, the goal of the language model is to output the sentence, the probability of the sentence, right? And a sentence can be represented by a sequence of words. Okay, say let's use the labels y1, y2, and y. Remember, this last capital T of y indicates the length of the sequence y. Okay, and this one within the brackets in the sharp brackets means this is the first word, which is at the first time step, and the y2 is the second word, right? Okay. All right. Let's see how we can build a RNN-based language model. Okay. So, of course, we will need a large corpus or a training set as a training data set. Okay. And for each sentence, we will first tokenize it. And to tokenize a sentence means we basically split all the words, right? We split a string of words into a list of words, right? So on the wall, I see a picture as a training example. Usually what we can do is to append a special token called the end of sentence, okay? Because we also want to predict when that sentence ends, right? If we don't have that special end of sentence, the predictions is never gonna end, okay? Right, and now we will use the technique, the one-hot encoding technique that we talked about last time, right? And we need to use the indices of each word in the vocabulary to represent each word. Okay. For example, the article word a, it is the first word in the vocabulary, right? So we will mark this index for the y6 is 1. Okay. All right, let's look at two stages. First, we'll look at what would happen in one training step. Okay, let's see, this is the input, right? So we list the vocabulary, which means we have 10,000 unique words in total in the training sets, right? So this vector is a very long vector, right? A very long dictionary. Okay, so let's look at the first time step of the training stage. And let's look at the inputs here. The inputs for x1 will be 0, and the 0 is also a special token because in our convention we let the first word be index 1, right? The second word be index 2. So the index is 0, which means this is a start of a sentence, right? So in the model, in order to let the model generate something, we will feed it something randomly as the as the random inputs, right, to jumpstart the model, right? So we will feed 0 to the RN model. So it will take 0 as the context to generate the first word, okay? And also for the activation layer, it will be 0 because there's no historical information yet, right? This is the first time step. All right, then we will generate, the model will generate something as outputs. Okay, so we call this y hats, and we can imagine that y hat 1 is not necessarily the word on, right? Because the model is not trained yet, right? If we are training the model from scratch, then the model actually knows nothing about human language, right? So it is very likely that the y hat 1 is a very randomly generated word. Okay, it could be any word among this vocabulary, 10,000 words vocabulary. Okay, but it's okay because we are training a model. Okay, so the y hat 1 is actually a probability. Okay, it's the outputs from a softmax layer. Okay, so y hat 1 is a probability that's have a probability value for each word in the vocabulary. Okay, and this y hat 1 will be compared with the ground truth, right, which is the 1-hot encoding of the word on, right? So now it's a typical classification problem, right? It's not a logistic. It's a softmax regression or a multinomial classification. So, but based on our previous knowledge, we know that we can compare the difference between the y hat 1 and the y 1 using the cross entropy loss, right? And the cross entropy loss is basically in a similar format as the logistic regression loss, right? Anyway, we can compute the gradients for this time step, right? So that's something we have put together. We have reviewed in a convolutional neural network, right? So that is the first time step. So the next time step would be interesting because now the second time step, we want to predict the second word, right? But we're gonna, the second word will have context, right? The second word, the, actually has the context word on before it, right? So what? So for the input of the second time step, we will let the word on be the inputs at the second time step. Okay, so x2 in the sharp brackets will be the first word in the ground truth. Okay, so this is a special place with recurrent neural network structure, right? Because we used part of the ground truth as the inputs. Okay, yeah. So the other things are the same. So the activations from the previous time step will be carried on here, and in combination with x2, we will make the prediction at the second time step. Okay, and let's call it y hat 2, and this is also a distribution, right, of probabilities. Okay, and the way we wrote these probabilities is that we put on as within the condition. Okay, on the right. Yeah. So I see. Matthew, you have a question?
Yeah, so does x2, is it already set to on, or is it just set to the value that we predicted it would be in y hat 1?
It is not the predicted value.
Okay, so it's given the correct value. Okay,
yeah,
thank you.
Yeah. We give it the correct value. Okay.
Okay, thanks.
Yeah. Yeah, but the mechanism, so the mechanism of feeding y hat here will be useful not in the training stage, but later in the testing stage. Okay, so we will mention that in the next slide. Okay, so now the specialty about these probabilities is that they are conditional probabilities. Okay, because we used the first time step the ground truth at the first time step as the inputs. So those probabilities knows that the first word is on, okay? So the meanings of the y hat 2 are actually conditional probabilities. All right, and for the next word, we take the same trick, right? We use the same trick. This time the context will be the, right? The input will be the, right? Because it's the second word before the third word. All right, we do this until we have reached the end of the token, okay? So the last token will be the one we want to predict, and the context of it is picture, right? Picture will be taken as the input. So now we will have at this time step, we will have a bunch of conditional probabilities for the last token, right? And this y hat 8 will also be compared with the 1 hot encoding for this EOS in order to compute some loss, okay? So as you can see, our context grows longer and longer, right? At the beginning, there's no context, and then there's one word context, and then 2 words, and until the end, we have a complete sentence as a context, right? Right, and this concept of context is more actually theoretical, right? Because it's based on the assumption that the RNN can include everything in a sequence previously as the context information, okay? But that is not necessary. That is not theoretically, it's not strictly true, because we said we will use back propagation through time, but with truncation, right? If we truncate the back propagation through time, then we are not including everything before the current time step, right? It's just within a limited window, right? But on this example, I'm just showing the theoretical meanings of the context, okay? So that's for the last time step, okay? So that's one training step. We will feed our training data. Like this is just, this whole thing in the blue color is just one training set, one training example, okay? It's just a one Y1, for example. It's just a one sentence as input. So in the training set, we can have hundreds of thousands or millions of sentences. We will feed all those sentences to the model again and again for several epochs until we have a sufficiently good model obtained, okay? So in the next slide, let's look at how we observe the performance, how we measure the performance of our language model. And that is to say, we will we will ask the model being trained to generate some sentences for us. And we will need to measure the probabilities of the sentence being generated, okay? So let's say after the training is done, right, we can use it to generate some sentence, right? So let's say the first word in the first step of generation, compared with the previous slide, everything here are the same, right? When generating the first word, there's no context, so we will let the inputs and the activation being 0. So y hat 1 will be the word being generated. So it's actually a bunch of probabilities. Okay, so what we can do is to retrieve. Okay, so I think I made a mistake. So this step is not for generation yet. So so in this step we are testing the probability of this sentence with the model that we've trained. Okay, so it's not generation. I think I have a slide in the future. In the several slides ahead, we will see an example for generating sentences. Okay, so here we are not generating sentences, but we are measuring the probability of a given sentence, right? The given sentence is also ground truth, right? So, and just for simplification, we contained 3 words only in this sentence, okay? So you see the first step, it will output, the model will output the probabilities for all the words in the vocabulary, including the word I, right? I put it here. And in the second step, the input is still the first word ground truth. It is the word I that we put into as a input, okay? And the output will be the probabilities for all the words, given that the first word is I, right? The difference is that here, it is after the training is done, right? So we are not using this probability to compute loss, right? There's no loss computed. There's no back through propagation carried out, okay? And for the last word, okay? So given these 3 probabilities, what we can do is to look at the probabilities of the first word being I, right? And the probability that the second word being love, given that the first word is I. And the third probability is the probability of the third word being you, given the first words are I and love, right? So now we just use the products. We multiply these 3 probabilities together and use the product of probabilities to represent the probabilities of the whole sentence, okay? And this assumption is that our language production is incremental, okay? So it's like we will generate the first word and the second word and last word, yeah. But this assumption, whether this assumption is true is a different question. It's actually a very tricky, very deep question. It's like whether we whether we will generate some complete representation for the whole sentence as a complete meaning, right? To represent the whole words we want to say, or it is more incremental. We will think of the first word before we think of the next word, right? So it's a really a complex cognitive science and linguistics and philosophy question, right? But so in order to have the machine being able to generate sentences, we will take the simple assumption that it's a incremental language generation process. All right, so it is basically the chain rules of probabilities, right? To compute the probability of the whole sentence, okay? So the rule of thumb for measuring the performance of a language model is that if a language model is good, then it should produce very high probabilities on the unseen test data, right? If those probabilities are not that high, which means the model is not actually able to model the natural language, okay? So other than the probability, we will use the different term perplexity, okay? But the perplexity is basically a numerical conversion for the probability, okay? So, but it's there's an inverse proportional to the probability. So we want high probability means that we want to low perplexity, okay? And this perplexity term is more oftenly used in academia to measure the performance of models, because this number is basically within a more readable range. It's not like the probability, which can be very small, right? Really small, really hard to compare with. All right. So I think we can go back to the example that we have shown 2 slides ago. Remember, on the wall, I see a picture versus on the wall, I see a picture, right? So we can basically use that language model to basically tell the to inform the speech recognition system that which sentence is more likely. Okay, so here's a system overview of where language model can be used in the speech recognition system. Like in the speech recognition system, we will take the raw audio wave as inputs, right? And we will convert it into some numerical representation, right? And this representation will be fed into a decoder, which wants to, which will decode words out of from these numerical representations, right? And the during the decoding stage, here we said the language model will be used together with the acoustic model. Okay, so the language model models the probabilities of the words given the previous words. Okay, let's say let's look at this example here. Okay, so I like to see, here's the input, right? I'd like to have some apple and pear, right? But the audio representations for these words actually doesn't differentiate 2 possible words for the sound pear, right? Like it's like it could be a fruit pear or it could be the noun pear, right? But what we basically can do is to use the language model to measure the probabilities of the words pear appeared after the previous words, right? So it makes sense to see that the fruit pear have a higher probability because it's after another fruit apple, right? And the whole probability of the whole sentence would be more likely than the second example. So in this case, the language model is helping or the speech recognition to disambiguate among multiple candidates' outputs, right? And going back to the example we have seen, it's the difference between on the wall I see a picture and on the wall I see a picture, right? So because a pure acoustic model here, right, given those 2 similar sounds, it hears picture and picture. Sometimes it's not easy to distinguish between the 2, right? So the language model can provide some additional information other than the pure acoustic information. It provides the probability information regarding the previous words, all the previous words in the output sequence, right? So in this particular example, the picture will be more likely than picture. In a similar way to this pair is more similar than this pair, right? Okay, so that's the application of language model in speech recognition tasks. Okay. All right, so that is a complete example of RN-based language model. And the model is based on words. The basic input unit is a word, right? So, but we know that a word consists of characters, consists of letters, right? So, and a word itself is also a sequence, okay? So yeah, so Brian asks if I can explain the good model would give the highest probability on answer. Yeah, okay. Right. Okay. So the word highest is probably not literally the highest, but the basic meaning is that a good model should produce a pretty good, pretty high sentence probabilities. So that is because the testing data, right, they are actual sentences spoken by human beings, produced by human beings, okay? So our goal is to build some model, to build some language model that mimics the behaviors of human language, right? So if a model, we say we have two models, A and B, right? And the model A produces sentences that have higher probabilities than the model B, then it basically says that model A behaves in a more similar way to human beings, right? To the way that human beings produce language. So that's why we say the sentence probability is a good way to tell how good a language model is. Okay. So it's based on the assumption that we can use the probability to measure the similarity between the model and the actual human subject that is being modeled. Okay. All right. All right. So let's look at an example. Because I like to pick up where I've stopped here. So we say the current example is words based on words, right? We split the sentence into several into the sequence of words, right? And the words is treated as the basic semantic units, right? So because word itself is also a sequence of letters. So, and in practice, we actually can apply a finer finer language model, which is to use the letter as the inputs, right? As a basic units. So I will have an example 1 or 2 slides later to show that actually character-based language models is also sometimes useful. Okay. All right. So before that, let's look at this Engram language model. So it's basically a traditional technique that the industry or the academia are used most oftenly, most commonly before the recurrent neural network is being developed. Okay, and the way that our Ngram-based language models, the basic principle is to estimate the probabilities using simple frequency counts. Okay, so it's a straightforward idea, right? Because probabilities in mathematics, how probabilities are estimated, like the probability of a random event, like if you toss a coin, how much probability do you have to get a tail versus a head, can be like estimated by tossing a coin for multiple times, right? You toss a coin for 100 times, 500 times, 1,000 times, and you count the number of head versus coin and head versus tail, so you get the probabilities estimated. So same thing for the words, right? Like if you want to measure how likely I'm going to say the word language, right? So you basically look through the whole corpus data and you count the number of appearance, how many times the word language has appeared, and use that quantity to estimate the probability, right? So And within the sentence, this technique is also used, like to measure the probabilities of the words of the next word given all the previous words. Say on the probability of the word picture given the previous 5 words, which is on the wall I see, right? So that is all the previous context. So what, in theory, the frequency count-based method needs to count how many times this whole phrase on the wall I see a picture has appeared in the data, and use this number to divide by the count of the shorter frame on the wall I see up, right? So that is the context. So this is mathematically, it is well defined because that is the definition of conditional probability given the next event being pictured, given all the previous events, right? But the problem of this is that it is very hard to observe the complete phrase, like on the wall I see a picture, to appear more than twice in a corpus, right? Even if it is all frequent, very frequent English words, but this sentence with a specific meaning is not likely to appear to be spoken by 2 different persons in different contexts, right? It's a very specific example. So we need to deal with this issue in using some technique called Engram model, okay? So for example, if the n equals 2, then the Engram model is a bigram model, okay? Which means we only look at 1 word ahead, 1 word in the past, okay? Right, so when we measure the first word being on, we will count how many combinations with the start of the sentence. So this is a special token for the start of the sentence. And this /s is the end of the sentence, right? This combination of s followed by on and use the count divided by the count of the starting sentence, the starting symbol alone. So that quantity is the probability, estimate probability for the first word being on, right? So similarly to all the words in the sentence, we will only look at the 1 context word before it, right? In the last example, picture, the probability of the word being picture given 1 context ahead, right? So we will not look at the whole thing ahead, right? Because that is too sparse, right? There's only 1 data points in the training set, right? But the bigram models, the bigram frequencies are much higher, right? It's very likely to see, for example, the combination a picture elsewhere, right? It could be a picture anywhere else, right? Anywhere else in other sentences. So these counts is much easier to estimate, to being non-zero, okay? So having these combinations, having these bigram probabilities being estimated, we can simply use the multiplication between these bigram probabilities to approximate the assumption, to approximate the probability of the whole sentence. And of course, this approximated probability is not accurate, right? It is not accurate because we are using the bigram probabilities rather than the actual probability, right? So it's an inaccurate estimation, but sometimes it's just sufficient for usage, but for different purposes. And of course, performance-wise, say if we use this model to measure the perplexity or probability of some testing data sets, it's usually worse than a neural language model, because neural language model can take into more context information rather than this bigram model. Okay. So this is based on the so-called Markov assumption, which is that the probability of a word depends only on the previous word, right? So this is a very simple model because in theory, the context can be longer, right? We can extend the model to a trigram model by adding, by looking at 2 words ahead, right? 2 words before. So similarly, same thing can be used for this trigram language model, and or even longer model. Okay, longer context like 4 words or 5 words before the current word. Okay, so the advantage of an Engram language model is it's easy to train, right? It's faster to train on a language model on the data sets because there's no forward pass, backward propagation involved, right? And it's just a count of words, and it can be optimized by implementing through using some lower level computer languages, right? And the disadvantage is that the context is sometimes too short, right? Even if we're using 4 context words or 5 context words, there's just not that flexible to capture longer dependencies beyond the context window, right? We're only using 5 words ahead at most, right? So as a comparison of the RN-based language models, if you look at the perplexities, right, and compared with the 5-gram language model, for example, that's a results from 2013, right? So the perplexities, which is the inverse probability, right? So we want a language model to have lower perplexity values. And we can see indeed, compared with all these Engram-based models, right, it will have much lower perplexity scores, right? So the disadvantage is that the number of parameters, right? You can see the number of parameters, it's much higher, way higher than these Engram language models. So particularly for these most simplest Engram language models, the number of parameters is just very few compared to the language model, to the neural network model, right? So in the neural nets, it's easy to get the number of parameters to billions or millions of language parameters, okay? And together, it's the training time that is in hours, right? We're using way more training time than the Engram-based language models. All right. So yeah, we get to the slide for sequence generation. Yeah, so for training time, it's language, a neural network can be optimized using the GPU. Yeah, that's correct. But the recurrent architecture itself is not friendly to. It's hard to optimize because the sequence for each input is different, right? And the recurrence mechanism means that we need to backpropagate through time for several time steps, and for the input token at different positions, that propagation through time steps would be a different value. So that makes the whole optimization more difficult, okay? but still it will gain some performance improvements using GPU, right? But as the paper reports, like 240 hours, that's you know, a lot of energy spent on that. So that paper is a 2013 paper. So nowadays, I don't think people will compete on building language models, recurrent, especially recurrent neural network models that have lower perplexities, because you know, you spend too much time and money, and you just want to beat the state of art perplexity to lower it by even less than 1%, and that is not just a reasonable choice. Yeah. So a disadvantage of trying to optimize using GPU. Yeah. So recurrent neural network is not. I would say it's not easy to optimize because as I said, the difficulty in making everything parallel, right? But since it's a neural network, it has weight matrix, it has weight multiplication involved in each computation. So as long as you have matrix computation involved, you can always use GPU to optimize, right? So I think that's after the year of 2015 or 16. There's a track of research in academia called green Nlps, which is to study the energy costs for large neural network-based NLP models, because back at the year of 2013, there's no huge models like transformers developed yet, but it's after 2018 or 17, I guess, the transformers-based models they have even higher number of parameters compared to recurrent neural network. Okay, so the energy cost is a problem, and it also requires very good GPUs. It's not like the gaming GPUs that we are talking about in those papers, in those research, but it's like I guess nowadays people use NVIDIA V100. It's very commonly used GPUs, but still, in order to train a model that have transformers involved, it's still a lot of time. Yeah. So I just read a paper by Microsoft. It's a hybrid model that takes the video clips as inputs and together with the subtitles of a TV show, but that's a lot of transformers involved, and that's actually a lot of training time required on not just one single GPU, but also on hundreds of GPUs, trained for days, even weeks on hundreds of GPUs. So I think it's an architecture problem. So for short, it's like the RNN's architecture is not easy to optimized by the parallel mechanism in GPUs, right? So if we cancel the recurrence mechanism, if we don't use mechanism architecture, for example, we just put convolutional network, and like in transformers, the so-called self-attention is just a bunch of matrix multiplication, but there's no recurrence mechanism involved, then it's much easier to optimize, right? Right. Anyway, let's finish these topics for sentence generation. So in sentence generation, I think I have this similar figure plotted when we first talk about the architecture, different architectures for recurrent neural network. So it's a special architecture that's used the previous outputs as the next inputs. For example, we are generating a sentence, right? And at the beginning, there's no context. So the X1 and A1, they are all 0, right? And we're going to produce a bunch of candidate words we have a probability produced for each word in the vocabulary. So we're gonna pick one, right? We can randomly sample from this distribution as the first word being generated, right? So for example, we pick the word the, right? Based on some method, right? And what we can do is to input that the into as the inputs for the second time step, okay? So this time, the X2 is not from some external ground truth, right? Because the task is to generate something from 0. We are not comparing with any ground truth, right? So the word generated at the previous time step is directly used as the input for the current time step. And we will have a y hat 2. So the y hat 2, the meaning of y hat 2 doesn't change. It's the conditional probability of all the words in the vocabulary, given that the first word is the, okay? So the context is always important in language modeling task, right? And then, for example, we still will sample some word, like we can pick the, so for the second time step, we usually pick the most likely word, okay? Or if we can like set a threshold to choose a bunch of candidates for this time step, and we choose the, and then we random sample among those most likely candidates, okay? So for example, we sample the second word being president, okay? And we feed the word president to the next time step, and it will generate a bunch of probabilities. For example, it's the verb is that we pick, okay, until we get the last sentence, right, the end of sentence. And the whole generated sentence is that the president is giving a speech, okay? So these generated a sentence, it makes sense semantically, right? It follows the subject verb object grammar, and it's basically it just reads naturally, right? Because the model being trained can successfully capture the probabilities, can capture the probabilities of the next word being all the previous words being said, okay? All right. That's a complete example for sequence generation, okay? So in this post, it's actually a famous post that explains the mechanisms of recurrent neural network. So we can actually use such a recurrent neural network-based architecture to generate different genres of text, right? Like these text on the left is the results of first training a language model, and then make the model to generate from scratch. So it's the model trained actually has encoded the styles of Shakespeare's rights, right? And more interestingly, like if we train a model on the use the latex code, right, as the inputs, and the model actually can generate some fake code. And in this example, it says according to the post, it's almost compiled, right? So it actually brings the question that actually the sequence that we wrote, no matter what kind of sequence is, like the natural language, like music, like even like computer source code that we wrote, they all have like temporal information that can be modeled by a sequence model, such as recurrent neural network model. Okay, although the sequence model, the sequence information is not 100% accurately captured, right? But still, some characteristic part can be captured. Okay, for example, still in the same post, they even use the character-based language model to generate source code. I don't think their code will actually compile, but it looks serious, right? Looks something that is organized, right? All right. So here we are at this point to cover this character level language model. So it's an interesting comparison with the words-based models, because the difference is that we use one character at a time to as the inputs, right? So we can think of the advantage of this technique, right? So if we are going to model letters instead of words, then the letters are much smaller sets, right? Much smaller finite set, other than the words. If we're considering all the possible words, then it's very easy to reach a thousands, or tens of thousands, or hundreds of thousands of unique words in the training set, right? But if it's letter, then it's just the basic composites in a language, right? So yeah, maybe a different case for different languages. In Chinese language, for example, the letters actually, the character that's we use in Chinese language is actually the basic semantic unit, but it has a very large set of basic characters, right? So a Chinese word can have a single character or two characters or even three or more. But since the basic units can be think of as characters, so the difficulty for modeling words was using words versus character-based language in Chinese is basically the same, I assume. But it will be a different case for English. For example, we have 26 letters. If we want to include case, then that's 52, right? So that's a small set. And we can also include all the other special symbols, right? Like the space, like other special letters, other symbols, non-letter symbols, numbers, right? All this, everything considered, we can still have a very small set, okay? So in this example here, our vocabulary can be very small, right? We can just include the letters, numbers, all the special symbols. Then that'll be basically useful, because it's very easy to deal with something that is outside the vocabulary. If we are going to use a words-based language model, then the whole model may not that good in measuring, in evaluating unseen words, like those foreign numbers, the foreign names in English. If we train a model, for example, in pure English data, then these not commonly seen last names, right? It's never seen by the model. So the model will basically treat these as out of vocabulary tokens. So the perplexity would be much worse. Okay, but if we are modeling the whole data, if we are designing a model to modeling the sequence of characters, sequence of letters, then all these letters are recognized, right? All those letters can be recognized, and the sequence is there, and there's something the probabilities can still be computed. Okay. So the disadvantage is also there, because you see the simple sentence that have 3 words, right? I and the love and you, right? That's just 3 words if we model it, use words-based RNN. But if it's characters, then we need to model this sequence with 10 input tokens, right? So that's much more expensive, computationally speaking. Yeah. I see a comment. Assume proper nouns would be difficult. Yeah. So proper nouns, when you have the proper nouns that only appeared very few times, right? So language is a a very messy data to model. So for proper nouns, we usually need the model we need to have a separate model to predict whether the current letter is within a proper noun, right? So whether it is the start of a proper noun or within the body of a proper noun or the end of a proper noun. So these are very detailed NLP tricks, NLP techniques. Yeah, let's see if I have more. Yeah, so I think we can actually stop here today. And in the next lecture on Thursday, we can cover the gated recurrent units. We're going to talk about why gates are necessary in modeling sequences and what are the shortcomings of the non-gated recurrent units. And of course, the 2 typical examples, LSTM and the GRU, will be talked about. And I can also give some examples of how how recurrent neural networks can be used in PyTorch. Okay. So that's it for the lecture today. Yeah. If you have any questions, you can let me know.